So what I'll talk about today is more of not an overview of recent work. I mean, there is recent work I'll talk about, but more like forward-looking, how I see recent machine learning tools like GFlowNets could transform scientific discovery and causal discovery and biology potentially. So that makes me very excited, more than I've been in many years. Scientific discovery in many ways is, you can think of it as searching needles in a haystack. So on the one hand, there is the space of experiments that we would like to do, but we only have very few that we can actually run. And such a space is actually so large that we can't even enumerate it. Even just thinking about the number of single small compounds that could be a drug, for example, it's like 10 to the 60. So there's no way we can do that. So we'll need other ways to explore that space. And not just by enumerating in a computer, because even that can't be, but using generative models or reinforcement learning to propose things. It turns out that the same kinds of tools that can allow us to search in the space of experiments can allow us to search also in the space of theories, right? So when you're doing science, you're doing experiments, the point of collecting that data is not necessarily just to come up with a predictive model. That's good. That's what we usually do in machine learning. But sometimes we like to come up with maybe more structured models. Think of the kinds of theories that scientists come up with. And again, that space is huge, right? All right. So I mean, to be concrete, think about causal graphs as an example of a theory that could explain the data, and the space of these graphs for, as soon as you go beyond a few variables, becomes just exponentially too large to be enumerated. This is related to lots of work in machine learning, but and also in computer science in general, in optimization, for example. Black box optimization has been around for many decades. I'm going to argue that we don't want to really do black box optimization, but rather exploration. So think about, you're trying to find a drug that has some property. Now, it looks like it's an optimization problem because you're just looking for the one thing that's going to work best. But I think you're better off thinking of it like as an exploration problem, because there's this really large space, and you probably don't want to just find the one candidate according to some oracle or some computer simulation, or even like think of in vitro experiments that works best according to that oracle, because that oracle may be imperfect. For example, in drug discovery, well, even if I have something that works well in vitro, or even worse in my simulations, it doesn't mean that it's going to work well in vivo, or even worse in humans. And so it's really important that we come up not just with one solution, but many solutions. So I'll talk about diversity as an important desiderata here. And so mathematically, one way to talk about this question of diversity is to say that instead of optimizing f of x, looking for x that maximizes f, maybe a formulation of this is not exactly what we want, but we'd like to find the modes of the function f, and the regions that are different from each other where f is large, right? So that's what the modes mean, the modes of the function of a function. Instead of the argmax, we want like all the large values that are somewhat separate from each other. Another thread in machine learning that we're going to borrow from is active learning, because if you think about the experimental cycle that I'll come back to in science, there's the question of which experiment to do next. So this black box optimization or black box exploration, the crucial question is, what's going to be the next X that I'm going to try on F, the oracle? And traditionally in active learning, a lot of work has focused on the case where you can just enumerate all the possible x's and then use some scoring function to tell you which one you should actually run. And as I said at the beginning, we're interested in spaces that are so large that even the computer can't enumerate them. So we'll need to do something else. The other important thread in machine learning and statistics that we're going to try to connect here is with uncertainty. As you know, many of you probably know, we need to be careful in distinguishing two kinds of uncertainty, two kinds of errors, if you want, made by a system. There are the errors that due to the fact that there is noise in the world, and that's what you could call irreducible uncertainty. And it's called aleatoric uncertainty. And then there is the rest, right? So what would be reducible uncertainty if you had more knowledge? So epistemic uncertainty, epistemic, that's knowledge. If you had more knowledge, more compute, or whatever, in principle, it could be reduced. But then there is also this interesting category, which is kind of both. So think about something that there's no noise, it's deterministic, but it's so complicated that there is no way, a machine learning system will ever, or in a reasonable lifetime, be able to figure it out. So think about making long-term predictions in a chaotic system. It's deterministic. If I redo exactly the same experiment twice, I will get exactly the same answer. I know the system is deterministic, but it's hopeless. Like there's no reasonable computation that will give me the answers. And so should we consider this to be aleatoric uncertainty or epistemic uncertainty? So my answer to this is we should put it in the category of irreducible uncertainty, but it's not noise. It's just not reducible because of computational limits. And so what we really care about in scientific discovery, experimental design, and so on is epistemic uncertainty. We want to go and do the experiments that are going to improve our knowledge the most, that are going to reduce the entropy of our knowledge. If you think of our knowledge as a random variable, because we're not sure of the true reality, we want to reduce that entropy as much as possible. All right, going back to diversity, I said that already, so I'm going to skip it. Okay, so let's go back to this question of sampling the modes of a function. So we're going to think of that function as a reward function because we want maybe to find high values of that function. And so if we had such a function, for example, think of a neural net that predicts the affinity of a compound, of a candidate compound with a target protein. So we've got some proxy for what we care about. We have it maybe in the computer, or maybe it's actually a black box that's an experiment that's going to happen in real, for real. But in any case, there is this black box function R of x, and we'd like to find the modes. Well, it turns out that there's a simple trick that will roughly give us the modes. And that is if we were able to construct a policy or a generative model that would sample IID from the distribution that I call PT here, that is proportional to that reward function. All right, so imagine you have, say, 3 modes, and then I sample IID from a distribution that is proportional to that function R. Then I'm going to get, few samples from all of the modes if I throw, maybe 6 darts at this, and so that's kind of good. It's something that we can characterize mathematically, and in fact, there's a lot of existing methods like Monte Carlo Markov chains, MCMC methods, that do exactly that. You can give them an unnormalized density function or an energy function, which is the same thing. E to the minus energy is the unnormalized density, And then MCMC methods will provide you with a sequence of samples that eventually converge to the right distribution that you're looking for. But there are some problems. So again, if we want to get samples from that distribution P T of X proportional to R of X, maybe R is e to the minus energy. If you think in terms here, energy is not necessarily like chemical or physical energy, but I mean it could be. But in machine learning, it's just a way to talk about the unnormalized minus log probability, and so we could use MCMC methods, but there are two problems that are related to each other. So one is you get the right samples only after a potentially very long chain, especially if the distribution is very complicated. And in fact, if the modes of this function R are far from each other, so I illustrate this here, then it might be essentially intractable to sample from all these modes, or even like a large fraction of them. And the reason is that the way MCMC works, so you have multiple modes, and MCMC methods make small moves, small random moves that prefer to go towards higher probability. So they tend to stay in a mode, or once in a while they jump to a nearby mode. But to jump to a far away mode, they would have to make a lot of moves that each of them are unlikely because it doesn't go up in probability. And so the chances of actually making these jumps becomes exponentially small. And so you just don't mix between modes, as it's called. And so that's a problem, at least for a lot of interesting distributions that we care about. I've worked on, vision problems with MCMC methods in the 2000s and early 2010s. And this was a big issue. All right, so we came up with this framework we called generative flow networks, or GFlowNets for short, that we submitted about a year ago to NeurIPS and was presented last December. And the goal was precisely this: to come up with a method that would take advantage of machine learning to bypass some of the limitations that I just talked about of MCMC methods. So how could you possibly solve this problem? If you had asked me 10 years ago, I would have said this mixing problem of MCMC is just intractable. There's nothing we can do. I mean, the space is too large. How could I guess where the modes are? Well, we have machine learning. What is machine learning about? Machine learning is about generalization. So what is generalization? It's about guessing answers to questions you've never seen. So the question here is, where do I find an X that has a high value of Y? And so if we have visited a few modes, like the 3 ones on the top right, maybe the machine learning system can generalize, oh, there's kind of structure here. Maybe there is a mode at that intersection of the grid here that I haven't visited yet. So this is what machine learning is good at. And when we do MCMC, we leave money on the table by not taking advantage of the information in all the places we have visited to guess what we could do next. And so GFlowNets have been designed with the idea that we could amortize that computation, that sampling computation, by replacing that expensive sampling through a long chain by expensive training of a generative model that would learn to sample in the right places. Okay, so this is what roughly at a very high level the first paper does. I mean, it gives the basis, and we wrote another paper later that came out last November. We call GFlowNets Foundations, that goes deeper in the math of this, and considers a number of extensions. So how should you think about GFlowNets? The kind of machine learning method that is closest to GFlowNets actually are variational methods, if you know something about them. So you train a sampler that will approximate some desired distribution. So MCMC does that, but doesn't train it. You have to do a lot of computation each time. The variational methods do that. They will train a sampler, and they can even train the model from data. I mean, that's how they were designed in the first place. Whereas GFlowNets, in a way, you think of it like you're given a reward function, and so it's related. It's a bit different, and of course, a GFlowNet is also related to RL. It was conceived as an RL method that departs from regular RL in the sense that instead of trying to find trajectories, so these samples are going to be obtained in a compositional way. That's a very important property of GFlowNets as well, like a sequence of sampling steps. So instead of producing that trajectory of stochastic decisions to, say, construct a molecule, in order to find the one molecule that maximizes some reward, we want to find all the modes. So that's the sense in which it's a bit different from traditional RL, and it's connected to existing methods in RL, like soft Q-learning and max entropy approaches. But there are some technical differences that give an advantage to GFlowNets. So there are lots of connections with existing literature, right? All right. So again, what we can do with these things is learn to sample from a distribution given a reward or normalized probability function. As a side effect, we can also estimate probabilities or even conditional probabilities after you've trained. And a really important aspect of this, as I said, it's really meant to represent distributions over complicated compositional objects like graphs of molecules, or graphs that may represent causal graphs. You can sample continuous values, discrete values, but if you compare it to the existing generative models literature, the strength is the ability to deal with these discrete random variables, which is usually more difficult to deal with. And then another kind of particular aspect here compared to existing methods for discrete generative models like autoregressive methods is that GFlowNets allow you to consider a many-to-one mapping from the process of sampling to the object that you get. So for example, graphs could be sampled in any order. You can add edges and nodes and so on in any order, and they're all valid in some sense. If you try to do it in an autoregressive way, which is the more traditional way, you have to decide on a particular order, which is not necessarily obvious. There are also some nice properties of GFlowNets that I don't think you find in other generative approaches. They can compute marginalized quantities. So in terms of probability theory, that means you can calculate or estimate probabilities over subsets of variables if you want. So summing over a large number of configurations while keeping other things fixed. So that's another thing you can do with GFlowNets. In the initial paper, they were used purely with objects that were observed, like molecular structures, but really they can also handle latent variables. Okay, so what's the relationship between the GFlowNet, what I've talked about up to now, and neural nets? So the way that GFlowNets operate, I mean, what they actually learn is this transition probability or this policy that decides how to change a current partially constructed answer object. Like, let's say we want to sample a graph. What we're going to do is we're going to gradually add edges. So maybe we start with an empty graph, and then we're going to say, oh, let's connect node 1 and node 2, and then next step, let's connect node 2 and node 3, and so on. So each of those steps is going to be stochastic according to a policy that is the generative model of the GFlowNet, but it goes through these steps. We don't generate the object in one step. In fact, if it was in one step, the GFlowNet wouldn't be very interesting. What makes it interesting is really this compositional structure, this sequential generation aspect, because of the generalizations that come out of that sort of decomposition. And so what the neural net does here is just at each step, it produces a, like in RL, like it produces a probability distribution over the next actions that you could do, given the current state of the construction. So this is maybe this partially constructed graph. So, we can use something like graph neural net that takes the current graph, and then we come up with a scheme for representing and calculating probabilities for the actions. Like, okay, so we're going to pick a node, and we're going to pick maybe some new entity that we're going to connect to that node from a pool of possible entities, like say atoms or fragments in the case of what we've done in our experiments. So that's where neural nets come in. They do the actual work of representing, learning, and computing those probabilities that will allow us to sequentially generate objects like those graphs. Okay, so the NeurIPS paper has a number of initial experiments where we focus on the ability of these GFlowNets to sample a more diverse set of candidates, and we compare with MCMC methods that have been used to generate molecules, as well as a standard RL method called PPO, to try to do the same thing. And both, for different reasons, MCMC methods and PPO and RL tend to have much less diversity in the candidates. MCMC because of the mode mixing issue, and PPO because of the fact that what they optimize for is just find one really good solution. And because of that, it turned out, it depends on the setting, what you're looking for, but in those molecule generation search problems, we find that this diversity also helped to quickly find a larger set of good solutions. Yeah, let me skip that. A little bit later, so this is now January this year, we continued working on GFlowNets. Many of my students, like half of my group, is working on GFlowNets these days. And one of the first next papers that came out is one that improves on the training loss and training procedure that was proposed in the first paper. And this modified objective is called trajectory balance. I'm not going to go into the details of it, but just let you know that this kind of work continues. So this is a very new area, and as we play more with that, so think of like when GANs came out, we didn't know how to train them well, and then after a few years, people got the hang of how to do this right. Another paper came out in February about how we can use GFlowNets as a generic density estimation or a machine learning tool for learning probability distribution from data. Because in the first paper, as I said, we assume somebody gives us a reward function or an energy function, and then we generate a sampler, we train a sampler for it. But what if instead we just have data and we want to represent learn a sampler for a generative model for that data? So this paper proposes one particular way based on energy functions, learning the energy function to do that. Okay, let me now move to applications of GFlowNets, and I'm going to talk about two aspects in the context of the experimental experiment theory cycle in science, and in biology in particular. So what this figure is supposed to illustrate is this cycle where we have some real world, maybe experimental bench that from which we can get experimental results after we've decided on what are the questions we want to ask, what experiment we want to run. And after having run many experiments, we've got a data set. With that data set, we can train a world model. So I call it a world model by analogy with model-based reinforcement learning. Now, an important aspect here that's maybe different from many things you will find in model-based RL or machine learning is that we don't just want to train like by supervised learning to say predict outcomes given experimental conditions, but we want to also learn about the epistemic uncertainty I talked about before. In other words, we want to learn not just to make predictions that are going to be as consistent as possible with the data we got, but we would like to know about, in a way, how much uncertainty there is about a particular prediction. We'd like to know that, you know, there are maybe many models that are consistent with the data or for consistent with a particular question we could ask in that universe. And that's the estimation of epistemic uncertainty, and there are many ways to do it. All right, so once we have a trained that kind of machine learning system that includes epistemic uncertainty, so for example, you could be Bayesian about it, that's what I'm going to suggest we should do. Then you can train the policy that's going to do the experimental design. So for example, in Bayesian optimization, a very standard way of thinking about this is the upper confidence bound acquisition function. So what we do is we say, well, we'd like to choose experiments that have both a high value according to our predictor, a high expected value according to our predictor, but also a high uncertainty. Because these may be places where we can learn more. And there are many ways you can combine them. And I'll say a few words at the end about what I think is the right way. But so we can extract a kind of reward function from the world model that says, you know, if we were to do a particular experiment, how useful would that be from the point of view of like finding, you know, maybe a better molecule or a better answer to the questions we care about, including the fact that by doing the experiment, we're going to learn something we didn't know before. And so we want to take into account that epistemic uncertainty. So we can cook up a reward function for a policy that we're going to train. That's the guy on the left that imagines useful experiments. It's going to, this policy is going to be, you know, it's going to be important that it's exploratory, because remember, you know, we don't know what's going on in the real world. So we need to explore and go to places where we might learn more. All right. So so in this other paper that one came out in March.
Sorry, Yoshua, can I interrupt you with a question?
Absolutely.
So how do you then learn these causal mechanisms from the energy function?
I'm gonna come to that.
All right.
Yeah, sorry, I'm going slower than I was hoping. So in any case, we have a first paper where we use this kind of cycle that I talked about to explore the design of biological sequences in various problems, using GFlowNets as the engine for learning the policy. All right, and I'm gonna skip the details of those experiments, and now I'm gonna talk about causal models. Okay, so I talked about how we can use GFlowNets to propose experiments, assuming I have learned a good model of the world that captures uncertainty. So now that we're going to focus on that world model and the fact that we want to capture uncertainty about it. And the direction that I'm really into in the last few years, and that I think is super important, is and particularly relevant in science. For example, in biology, think about the gene regulatory network, which is really a kind of causal graph. So would like to not just build a black box predictor, but one that captures the causal structure and the data. And I don't have the time to give you a lecture on why causality could be useful, but in a few words, there are lots of reasons to think that if you're able to capture well, not necessarily perfectly, the causal structure, then you can generalize better, period. And you can generalize better, more importantly, out of distribution. So in settings that are quite far from what you've seen when you train the system. This is something where current machine learning is not good. We have this huge models trained on huge quantities of data, but when you test them somewhat far from what they've seen, they fail often. And it's also interesting to see the ways in which they fail. They fail to reason, and I use the word reason as the kind of things that humans would do to combine pieces of evidence that they know, but in new ways. So there's lots of good reason for building that, our world model structured around a discovery of the causal structure and even the discovery of the causal variables that explain the data. So what we see in the figure on the right is the sort of general setting of these experiments is that we can do intervention. So the X here is, as before, it's the experiment. It's what is it we're going to do, the specification of the experiment, but you can think of it from a causal perspective as an intervention that's going to modify something in the dynamics. For example, if I do a knockout of a gene, I'm going to change the dynamics of the cell. And then you have the actual causal structure. So let's say the variables here could be the amount of expression of all the genes. And there is some graph that we don't know. I mean, we have some clues about it, but by far we don't know enough of it. And we'd like to figure out what that graph is. And that it's not just the structure of the graph, it's also how the different variables, say the expression of different genes, interact with each other. So it's also quantitative. Okay, so there's a discrete thing, which is the structure of the graph. Is there an edge or not? And then there is, think of like some numerical relationship. Maybe there's like, think of it, we're going to model it with a small neural net that will capture how different parents in the graph affect another variable, which is going to be a child of these parents. And then there's a third component. Even if I was good at capturing this Z, I might not be able to measure all of these things directly or precisely. So there's going to be some space of experimental measurements. Maybe it's maybe it's going to be noisy, maybe because my measurements are imperfect, or maybe it's worse than that. Maybe the outcomes are images. I mean, there's a lot of biology now that's done with high throughput microscopy, for example, and we can look at those cells and get all kinds of indirect clues about what's going on there, but it's not the underlying causal variables. So there's this other mapping, other like conditional distribution that we need to learn that maps the causal variables Z to the outcomes Y. Now, I'm going to now focus on the text on the left. So one of the central problems in causality theory is identifiability. The problem that in most cases, we're not able to figure out what the causal structure is. And most like reasonable, like realistic cases. And it gets worse if we don't observe those causal variables. So we just, say, well, we can't do causality, or we could take, I think, a more machine learning stance and bite the bullet and say, there's going to be some ambiguity. At the end of the day, we're not just going to have one graph. We're going to have a distribution over graphs and a distribution over these, the distribution over the relationships that link those variables together. And that's the stance that I think is the right one. And there is a mathematical tool that provides us exactly with that. It's to model the Bayesian posterior over the causal models, say the graph and the mechanisms. So what does that mean? It means that instead of delivering one graph and one joint distribution between the Z's, so this set of mechanisms, I'm going to deliver a distribution over these objects, right? And if you had asked me 10 years ago, I would have said, oh, these Bayesian methods, they're like theoretically nice, but they don't work because either it's too computationally expensive, like MCMC, like on large scale, is just not going to work here, or you have to make these outrageous parametric assumptions that you typically find, for example, well, either in very simple parametric models that clearly don't fit the kind of data we have, or in variational methods that are closer to what we want, but typically also assume, all kinds of, conditional independence or dependence assumptions that are outrageous. So I thought, okay, we can't really solve this, but it turns out you can do this. Well, it turns out we still have to prove it, but I'm pretty sure I'm going to try to explain quickly that you can do these things with GFlowNets. So we have a first paper in that direction that is to be presented at UAI 2022. It's called Bayesian structure learning with generative flow networks. It's only a small step in the direction that I'm talking about. It only focuses on learning the graph. But some of the things we're working on now really involve generalizing this to learning also the mechanisms, and also in that paper, the causal variables are observed, and we also want to learn the mapping from interventions to how the graphs or the mechanisms change, and we also want to learn the mapping from latent states to the observations, the experimental outcomes. Okay, I'm not going to give you the math of how this works, but briefly, you can turn the problem of finding the posterior, which is a distribution that you'd like to sample from, into a GFlowNet problem of, you have a reward function and you'd like to sample from that reward function. And the reward function is basically just this e to sum of the energies of some model for the data that you have, and you can turn it into a stochastic gradient descent objective very easily. So it can be, you can basically train these things as easily as you train normal neural nets by SGD. I'm going to stop here and just show this link for people who want to learn a bit more about GFlowNets. I wrote this tutorial that you can find online.